In the next unit, we're going to talk about vectors. Vectors are a way that scientists use to construct buildings and determine whether the building is actually going to support the weight of each floor. Or vectors are used to construct bridges. You can also use vectors if you're an accident investigator and you are looking to figure out exactly how fast cars were traveling before they hit each other. Little did you know, but you were also using vectors already. Here is the racetrack that we did, and those arrows, each of them is a vector. Notice that the vectors point in a certain direction and have a certain length. Both of those matter. So down here at the beginning, you would have a shorter arrow representing a smaller speed in a direction on this that would seem like it would be north. Over here, you would have a different length, so the size matters, and then the direction that it's pointing would also matter. Those are all vectors that you did on that racetrack. So what we're going to do is we're going to talk about vectors first, give you a few definitions to get you started for the unit, and then after the definitions, we're going to talk about how to do directions for a vector. Lengths are pretty self-explanatory. The bigger it is, the longer it is, the shorter it is, the smaller the arrow is. So there are two kinds of quantities. One quantity is called a scalar quantity. A scalar quantity only requires a number to describe it. So we had been talking about the fact that speed and velocity are very close to each other, but there's one slight small difference between them. Remember, velocity needed a direction. Speed, if you'll notice on this list, is in the scalar quantity section. It requires only a magnitude. When I think of the word magnitude, for whatever reason, I think of an earthquake. That earthquake had a 7.7 magnitude. Just by the number, you kind of know a lot about the earthquake. The same thing with a scalar quantity. You don't need anything else to describe it except for a number. So you'll notice on there that time is one of your choices. If you were to adequately describe time, all you would need to do is to give a number like 3.5 seconds. A mass is on this list. Again, just requires a number to describe it. A velocity, however, is a vector quantity. Vectors require two parts, both a magnitude and a direction. So you would need both to describe a vector quantity. Concurrent vectors, of course, as the definition says, there are vectors that happen at the exact same time. There is also a concept of vector independence, which means that even though we have vectors that are acting at exactly the same time, we can look at them separately and individually, and we can figure out exactly what was going on just by looking at them separately. In the whole entire situation. And I'll have a actual thing that I'm going to ask you to do here in a few seconds. Let me finish with the definitions first. The next thing is a resultant. A resultant is the actual movement. If you combined all of the vectors that were happening and you actually did them simultaneously or concurrently, what way would the object move, or how would the object actually be affected? It's the result of those things happening simultaneously. An equilibrant is the thing that equalizes the resultant. I think of it like a tug of war. So if the resultant goes in one direction, if you wanted to have a tug of war where the flag wasn't moving in the middle, then you would have something pulling with the exact same amount in the exact opposite direction. So now what I'd like to do is I'd like to do a little activity that involves some students in the room to demonstrate concurrent vectors, vector independence, and resultants. So at this point, I'm going to ask Mr. Farron to get 3 volunteers in order to help with this next demonstration, and I'm going to describe what I want the volunteers to do. So, Mr. Farron, find 3 people to help us out, if you wouldn't mind, please, and I will continue this in my next video.